Buenos días. Prueba de audio, video en Auditorio París para el coloquio 2016 de hoy, 16 de noviembre.
Quiero presentar doctor Adam Popowicz, él de Polonia, de Universidad de Tecnología de Instituto de Automatización y Control de Silesia. Entonces, él va a hablar de desarrollo de un software para procesar los datos de un instrumento espacial de satélite para ver objetos brillantes, pero él va a hablar solo sobre pipeline. Este es un software para procesar los datos obtenidos con este instrumento. Yeah.
Thank you, Valerie, for introduction. I'm really pleased to be here with you in this great country far away from my home in Poland. I would like to address my special thanks to Valerie for organizing my stay here 2 weeks. I really hope to see your beautiful sky at San Pedro Martyr. Hopefully the weather will be okay. I'm from Silesian University of Technology. It's not so big university as you have one here. I'm from Institute of Automatic Control, so we deal with all this stuff connected with informatics, electronics, and in general automation. Well, I had quite a dilemma before preparing the presentation, so I decided to show you probably the biggest adventure in my short career so far, and the adventure with BRIGHT nano-satellite mission. Actually, I didn't take a part in this project from the beginning. I was invited to help with some problems and to propose some solutions. But still, it's about 3 years of work in this project. So I was introduced to project in 2013. So it's three or more. Yes, I had a dilemma because I have a lot of interesting things that I wanted to present, but I decided on this one. Here you have the plan of my presentation. I will first show you a quick introduction to our mission, the overview, how the satellites look like, the internal structure, some details about launch, about ground stations, and then we'll go to the problems we have in our satellites. And as the answer for these problems are the pipelines prepared by me to process the data, which is actually very noisy. And we have 2 pipelines, as we have 2 modes of observations. Actually, now it's only one, but for 2 years we had another method of observing. So there are 2 pipelines developed for each observing mode. And I didn't mention it before, but I'm an electronic engineer, so I'm not astronomer at all. So I will limit myself to only read what kind of findings astronomers found in our data. There are some publications, and plenty of them are currently under construction. So at the end, the astronomers will see what kind of discoveries, findings you can find in our data. I will also encourage you to a collaboration in BRIGHT nano-satellite mission, but details about this will be at the end of my presentation. So the BRIGHT mission is the mission in which 3 countries collaborate. It's Canada, Austria, and Poland. It's because we have the same colors in flags. Oh, of course, I'm joking. It's not because, well, I thought that I should say that only the countries which have red and white in flags can collaborate with us. That's also not true. So this is a constellation of 6 nano-satellites, which are, well, let's start from the beginning. The project initiator was Professor Sławek Ruciński, who is actually Polish astronomer working in Canada. So we have those 2 countries connected by Sławek Ruciński. And also Professor took a part in previous very interesting satellite mission, which is MOST mission. And in this mission, he collaborated very strongly with Austrian scientists so that these 3 countries develop a new idea for observation of the brightest stars. Initially, Professor Ruciński suggested 300 brightest stars down to 4.5 magnitude, but now we know we can observe about 5,000 stars because in our data we can analyze the variation of intensity of stars down to about 7.5 magnitudes. So the main aim is precise and continuous observations with very high accuracy, below 1 millimagnitude. So the main aim is to observe some very small pulsation. It's connected with astroseismic. Again, I'm not astronomer. For me, it's just to have the accuracy below 1 millimagnitude of our data. 3 of our satellites are red. They have red filter. 3 of them have blue filter, so we have 2-color photometry for these stars. I'll start from the end. It means here is some overview. We have 6 nano-satellites, actually not 6, because one didn't detach from rocket and we have no response. So we have 5 nano-satellites. We have no idea what happened. We don't have any response from these satellites. So we have 3 red and 2 blue, actually, satellites. You can see the range of wavelengths. They orbit the Earth at low Earth orbit, which is from 600 to 900 kilometers. They orbit the Earth. The one period is 98 minutes. It's a polar orbit. Our field of view is very, very large. I will talk about it later, but just a first glimpse of us. We have 27-degree field of view. We take exposures quite short, 1 second to 5 seconds, usually 1 second exposures. And we can take about 50 exposure per 1 orbit. It means in 98 minutes. And it's because well, initially we wanted to have a photometry which is done on board. And in this mode, we could have a lot of measurements per orbit. But because of the noise which appeared, we have to download the parts of images to Earth and then process it offline. That is why we take about 50 exposure per orbit. And in one field, we observe up to 30 stars. And one field, a constellation, is observed for 3 months, then we move to another field. And after probably 2 or 3 years, we go back to the first field. So here is a view on internal structure. You can see our instrument is quite small. It's 20 centimeters wide box. In this box, we have our telescope, and we have star tracker, which keeps the satellites pointed right way. We have, of course, solar cells, and we communicate with the satellite using two antennas. One is UHF antennas. It's for sending information to satellite and to retrieve information about temperatures and not images. The images are sent with S-band patch antennas. So it's only downlink, and with these 2 antennas we conduct uplink and downlink. The original framework for these satellites was the generic nano-satellite bus, which was developed by University of Toronto and Spaceflight Laboratory, so it's by Canadian, during their research program, which is named as here. So originally, the whole structure was prepared, was designed by Canadians. Here is our optical system. We have several. We have five lenses. It's because you can see that our CCD sensor, its size, it's very close to the size of the telescope, and that is why it's hard to have good proportion within the field of view. The field of view is 27 degrees. It means that it's 24 seconds per pixel. So without defocusing, the star would be in a fraction of pixels. So this system is defocused. So we have very, unfortunately, you will see it, very complex irregular PSF shapes. It's one of the main problems in our data. A quick view on our CCD sensor. It's a scientific grade interline sensor which was produced by Kodak, and then the Kodak was sold to the TrueSense. Now it's actually on semi. So we have 11 million pixels. It's full frame CCD with these dimensions. 1 pixel has 9 micrometers saturation rate. Typical front illuminated CCD with 60% quantum efficiency in a peak. And you can see here that it was quite surprising for me, but the main idea was to make the photometry on board and to have a lot of images. So they want to do quick exposures. That's why the readout time is very short. For this matrix, it is really short. It means that the readout noise is also quite large, and the resolution is degraded from 16-bit to 14-bit. It was, as I said, because we initially the photometry was to be done on board, but now it's not done this way. You can see that the operating temperature of CCD is quite high. It ranges from 5 to 40 Celsius. And this sensor is unfortunately not hardened for radiation. And that's why a lot of problems appeared after the launch. I don't know the motivation why the team didn't buy the radiation hardened sensor, but I can guess that the problem was with the money, because usually the radiation hardened elements usually cost about 1,000 more times than a single element. So when we have quite low budget, because it's low budget mission, they decided to use scientific grade but not radiation hardened CCD sensor. A quick view on the electronic board. We have a temperature sensor below the CCD, and that was quite crazy. There are 4 heaters. Canadians they thought that they will be used to stabilize the temperature, that CCD will be heated, but it's not used at all. It was an idea, but we now know that we don't care about stabilizing temperature. We just want to have the lowest possible. So the heaters actually don't work now. It's an interline CCD sensor. It was selected, this one, because of the fact that we can have a lot of images, a very short readout time. A pixel of such a sensor is divided into light-sensitive part and transferring part. So during the collection, the light is collected in this photosensitive side, and then during the readout, the charge is transferred to the it is called vertical register, and then it is clocked to the horizontal register. Why this sensor was used is because, again, originally the photometry was to be done on board, and we wanted to have a lot of images. So this matrix allows for very fast imaging. But more important is there is no need for a mechanical shutter here. The designers were aware of the fact that mechanical shutter can stack, and that will be a disaster for mission. And in this CCD, during the readout, the charge is transferred to vertical register, so there is no smearing because the light is not collected. Okay, some launch details. We have 6 satellites. One is not responding. The first launch was 2013. The last here, not far ago, 2 years. And we used 3 organizations to launch the satellites: Indian Space Research Organization, our friends from Russia, Kosmotras, and the last one, the last Polish, was launched with help of China Aerospace Science. You can see the altitudes of our satellites, the inclinations, and the period is quite similar because it's polar orbit. It's also sun-synchronous. Ground station. We have 2 ground stations. The first is in Warsaw. The second is in Graz, University of Technology. They are the same. We have 3-meter parabolic antenna for receiving the images, the data, and Yagi antennas for telemetry, for sending information to our satellites. Okay, so when looking at the goals of our mission, it looks that, well, it's a great success because let's look at this point-by-point download rate. It is higher than expected. Fine pointing stability is also better. We have, I will talk about the data we have later, so don't care about this information about subraster. The magnitude range of objects is higher, so we can reach deeper. In some parts of sky, we cannot stabilize the satellites. It's because of the lack of good guiding stars for stabilization, but it's very occasional. Usually, we can stabilize the satellites quite well. We can observe about 30 minutes in one orbit, so it's the maximum value. It's when the orbit is, for example, 100 minutes. So for 30 minutes from this orbit, we can devote for observations because we can see the field. We also have large number of stars in one field that we can observe. And during one orbit, we can also switch between two fields. So for a part, we observe one constellation. For another, we can observe another. But usually, we observe one. And here is the clue. I think it's a very nice slide. I like it. It's our field of view with Orion constellation. And you can see the rasters here. We transfer only rasters around the stars. It's because one image is 20 megabytes, and we do not transfer whole images, only parts of them with star. So we have 15 stars here, and you can see how the PSFs are different one from another. Here is the outcome of using a drizzle algorithm on our PSFs. So you can see there are some spikes in our PSFs, and they are really nasty because we have problems with intra-pixel sensitivity variation. It means the pixel has different sensitivity depending on the place where you put this spike. So we have a range of shapes. It's because of the very large field of view, very small lens, comparable with CCD sensor and defocusing. So it results in such PSFs. You can also see some points. There are the hot pixels, hot or warm pixels that appeared due to radiation. I will talk about them in 3 slides. It was the first problem. It means irregular PSFs. The second problem is also that we have some issues with tracker. It means sometimes the tracking is not so good. You can see the rasters image from image to image, and the PSF moves around. Sometimes the images are blurred because tracker just did some movements. Sometimes the PSF is out of our raster. You can see here how it changes from frame to frame during 35 days of observations. Next problem is exactly the main problem. It's dark current. It was not visible at all before sending satellites. It developed in orbit. So there are two. It was due to the proton hits. The proton bombarded the matrix, and defects appeared in pixels, and the pixels started to develop dark current. So there are two types of effects. One is single pixels as hot pixels in dark frames, and there are also columns. It's because our pixel is divided into two parts: light sensitive and transferring. So if defect appears in this transferring part, then whole column is affected. So we can see brighter columns in our data. And sometimes, if temperature is really high, you can even not distinguish the PSF from the background. It's really noisy data. The dark current, it's not as it is in ground observation. In ground observation, it's easily predictable and can be compensated by using dark frame. The amount of dark charge depends, of course, on exposure time, on some constant, and on temperature. There's also the activation energy and so on. But it's the formula is known, and you can predict the dark current in a given pixel. Unfortunately, in the defects which appear due to radiation, the G parameter oscillates between many metastable defects. So you can never predict what is the current state of given defect. So it can produce different amount of charge. So it cannot be compensated by any dark frame correction. And the most nasty problem is charge transfer inefficiency. It developed several months or even a year after the launch of satellite. Whole region started to show such effects. You can see that there are tails after hot pixel, and also PSF is blurred. The problem is because of shallow defects which appear just under the electrode. Such defect, it introduces problems with transferring the charge. So the electrons, they don't manage to be transferred from pixel to pixel, and that's why these tails appear. So just imagine that we have so high temperature, and also add the problem of CTI. It's really the team was very surprised that data is of such low quality. But this problem with CTI was resolved. I proposed to reduce one clock of the CCD and it helped, but it took several months to find money to pay someone to implement it on satellite. So finally we got rid of those problems, but we have plenty of data with CTI effects. Okay, so now we'll go to the methods that were applied to to processing our data. Here is a final outcome. It's a light curve for a star. We can see that there are 70 days, so it's like more than 2 months of observations. Here, a closer view, you can see when we observe. Then we have the observation time is about 20 minutes, while the whole orbit is 98. So our points are clustered in so-called, we call them orbits. You can also see some gaps. It's because of problems with stabilization, so the satellite had to be restarted or something like this to work again. So we have some gaps in our light curve, but actually it's quite nice. About the accuracy, I will talk at the end of presentation. So, okay, we have 2 modes. I said at the beginning that we have normal mode and so-called chopping mode. In normal mode, it was the default observation mode, which was used for 2 years. But then we could see that there are so many hot pixels with temperature, when temperature is high, that we were not able to make any photometry with this. So I proposed to use a chopping mode. In chopping mode, in each next image, the satellite is reoriented slightly left, right, so that our star is moved from left to right in each next image. And using this frame, we can subtract automatically frame by frame and have so-called differential images. So we have 1 frame, second frame, we take the difference, and now in this we can work with these images. So the chopping mode is nowadays used in our mission. But I will show you both pipelines. First, because it was like 3 years we worked in this mode, so a pipeline had to be developed for this also. So the pipeline first for traditional imaging. Traditional, it means the star is the observations are exactly the same direction without chopping. We have several parts. First, image classification. We reject blurred images that take so-called pseudo dark frames. It means sometimes it appears that the PSF is out of the raster. So we make use of these moments and use these frames as kind of a dark frame. But actually, we don't do dark frame correction typical. I will show you what we do with this. Then we have image processing. It means we find centroid, interpolate hot pixels. We perform simple aperture photometry, and we have to decorrelate data because of problems with intra-pixel sensitivity variations. And we also perform optimization. So we select the best aperture, which produces the lowest scatter. Okay, I will show you by examples. It will be the best, I think. We have original raster, so 6 examples of raster with stars. The first, we want to classify images. We want to reject the images which are not useful for analysis. So first, we calculate the medians in each column, median intensity. This median intensity is reduced from raster. So we have column subtracted images. Then we take these images and we apply a median filter. A simple median filter which exchanges each pixel by the median of intensities of neighbors around. It slightly blurs the stars, but we don't care about this. We don't perform photometry on this. It's just for classification. And now, in the next stage, we perform thresholding. We know what is the range of the intensities of our stars, so we apply some single threshold, which is about 25 electrons, and it is okay. So we have the masks of our PSF. Actually, it's not done so simple. It's iterative because you can see that sometimes after the subtraction of these median columns, the PSF bias the median intensity. So these columns were compensating not correctly. We can see some dimmer parts here. So after median filtering and thresholding, we repeat the procedure, but we mask the pixels which were previously found as to be in PSF, and we calculate again median of columns and subtract it again. And this time we don't have this dim shadow here. Again, median filtering and thresholding, and is iterated as long as the mask evolves. Finally, it converges to quite nice mask of our PSF. We use this mask. In each image, we count the number of pixels which are in mask. It is the clue of classification. When we plot the number of pixels in a PSF in time, we can see that the points are arranged in about one value. It slightly can change because the temperature changes our PSF, so it can grow a bit. And also, the intensity of the star can change. It also can slightly change the number of pixels in PSF. But generally, we apply 2 thresholds. We do it manually. We tried different automatic methods, but manually putting the threshold was the best. And we take only the images which are within these bounds. The images which have larger star area, it is just an example. They are blurred. A larger number of pixels were detected as to be in PSF. If the number is lower, then probably PSF is out of the raster. That's quite easy. And if the number of pixels in PSF is 0, they are our candidate dark frames. We take them and we average them using simple median averaging. And we produce this way so-called master dark frame. So this is classification, just rejection of images which we don't want to analyze. And then we are going to have some photometric calculations. So we have our dark frames, master dark frames, because we have averaged them. Then we apply a threshold. So the threshold is one of the parameters which are optimized at the end of our pipeline. So we take one value, then we take another, and we look which scatter is, the scatter of light curve is the lowest. So in general, we apply a threshold. So we have pixels which are found to be hot. Let's say we have to interpolate them. Okay, so we have our rasters with all type of noise. Again, we applied compensating the medians of columns. Then we applied median filtering around each pixel. That's the same step as it was before. We have the mask, which is done iteratively. And then we apply this mask on this image, which is column. We found these bright columns. And we look for the pixels which are hot within PSF. And only those pixels are interpolated, are exchanged by the median of intensities of neighbors. And on such a thresholded and interpolated over hot pixel image, we calculate the centroid. But well, the exchanging the hot pixels with a median of neighbors, it's very easy, but for photometry, it's not very efficient. So I propose, well, I propose because we propose, I can say we propose, the method for better interpolation. This method utilizes the fact that the PSF fortunately moves around from frame to frame. So we can look at the PSF as it is located in different parts of our raster. So while the hot pixels stay in constant places, the PSF moves. So let's assume that we want to interpolate hot pixels in this first image. We have to know the centroids. Of course, we have calculated them before. and we calculate the relative shifts between the images. So it is very important because we want to have our PSF shifted by integral number of pixels. Why it is very important? Because as I previously mentioned, that our PSFs had spikes. So we want to have our quite complex PSF located exactly the same way on a pixel grid. We don't want to have the PSF moved by half of the pixel because the spikes can look different simply because of the intra-pixel variation of sensitivity of a pixel. And that is why we calculate so-called fractional shifts. It's just we take those relative shifts and take a fractional part of a shift. We want to have integral number of pixels in x and y direction. And we do the interpolation. So the estimated intensity of a hot pixel in our image is the weighted average of intensities of corresponding pixel. Corresponding, it means the same in PSF. It means the same relatively to the centroid position. Weights are taken from our fractional shifts. So if the PSF is moved by integral number of pixels, this intensity of a hot pixel will be taken with larger weight, while the PSFs which are shifted by non-integral number of pixels, the weight will be lower. So the intensity of a pixel taken to interpolation will be lower. And it really worked very good. We take 10 images from left and right, and we use the interpolation using only the closest neighbors in time. Now, another problem is that we have those intra-pixel sensitivity variation. We perform circular aperture photometry, but the problem of intra-pixel sensitivity variation is very significant in our data. When we have a spike, which is very narrow, and it moves around the pixel, because of the fact that pixel has different sensitivity on the edge than compared with the center, then the amount of charge will be different, depending on the place where the spike actually looks at. So you can see it in our data. When we have, for example, such a PSF, we can see that spike. The spike is very narrow, narrower than a pixel. Then when we analyze our errors, we could see that the error depends strongly on the fractional shift of our PSF. So when we plot the fractional position or the fractional position of a pixel of a PSF, and then we calculate our errors. In this is actually the error is deviation from median in orbit. So we have points in orbit. We calculate the median, and each point has its offset. So while for x-axis it is not very strong, we can also see that in x-axis there is no strong spike. For y-axis, the dependency is very strong. It is like, I don't know, 5 millimagnitudes. It's really a really large value for our data. So this is compensated this way. We calculate the median in orbit, median intensity of a star in orbit. We calculate the deviations, and we fit a 4th degree polynomial to our data and compensate our points by this curve. So we perform optimization. As I said, there are 2 parameters. First is the threshold, which was used to find the hot pixel. So we had the dark frames. We applied thresholding to locate where are hot pixels. So we can use different thresholds. So thresholds are the first parameter of our optimization, and the second is the aperture, the radius of our aperture. We use simple circular aperture in this data because it worked better than some customized shapes. And we have the optimal value. Our coefficients is, again, we use the fact that our points are arranged in orbits. So in each orbit, we calculate the spread using median absolute deviation. It's a robust way of estimating the standard deviation. And for each orbit, we have MAD, and then we calculate the median of this mass. And this is our coefficient. So this, in this particular example, we had aperture radius of 5 pixels, and probably the threshold of 50 ADU, which is about 12 electrons for finding the hot pixels. But after 2 years of observation, we switched to chopping mode, just because a lot of problems appears due to the CTI, which actually is resolved now, but we keep with chopping mode because it allows for better photometry. We hope to develop next pipeline for getting better results. So in chopping mode, it's a bit easier. The pipeline is much shorter, and the whole analysis also takes much less time. So we have in our data, we have the stars moved from left to right. So we have to reject some pairs where the PSF are not far enough. We have also to reject the measurements where PSF is out of the raster. And again, we calculate centroid, estimating that is new, estimating a high quality PSF shape, then aperture photometry. Yeah, we create various shapes of apertures, because in previous data the customized aperture didn't work well because we had a lot of type of noise. But in this data, as the noise is reduced by chopping, we can use customized apertures. But we also try in optimization circular apertures. So a set of apertures are actually in our optimization. We have to also compensate for intra-pixel sensitivity. It's the same way. It means the polynomial and so on. And in optimization, we only optimize the best aperture, which produces the points with a lower spread. So just an example, 2 images consecutive. We have differential image, and then it is the classification part. Then we apply median filtering. It's again to get rid of some white and black pixel. Why do they appear here? It is right because of the fact that the hot pixel changes their value. You cannot predict what will be the dark current in a given observation. So even if in 2 consecutive images in nearly the same temperature, the dark charge can change. So it appears as black and white pixel, but it's quite rare. So we apply median filtering, and then we have a thresholding. Again, it's a constant value. So the thresholded parts are the gray ones, and we perform dilation. It means the shape is slightly extended by 1 pixel. So this is good example. We will take this image because there are no problems. But in this, there are 3 conditions which have to be met to use image. In this example, all those requirements are not met. First, one of the pixels after dilation touch the edge of our raster. So if any touches, then it is discarded. Second, after dilation, they overlap. So the green pixels are overlapping, so they are too close. And also they are too close because of the centroid. We calculate on this image centroid of one and the second PSF, negative and positive, let's say. And we look for the difference between these points. So when we plot the difference between centers between the centroids, it looks like this. And again, this is done automatically. So our raster is 38 pixels. So we want to have the difference between the PSF in a specified region between 12 and 36 pixels, or other situations means that something is wrong. So here they are too close. Here they are too far. We have three conditions. So all of them has to be met. First, touching the PSFs one to another, touching to the edge, and the last one is the difference between the PSF. And all has to be met to use this image in our photometry. And so we have very good images. We have images which were selected. And then in each next differential image, we take the brighter, the positive PSF, and align all this PSF on much larger grid. We perform interpolation on this. So after averaging, we have a high fidelity, let's say high fidelity PSF. And we apply a range of thresholds. This way we obtain a range of apertures. So here we have 15 customized thresholded apertures. And we also use 10 circular apertures to try which one will produce the best results. So in total, we have 25 apertures. We try each of them and look what is the quality of light curve. And here you have an example. Here are 15 thresholded apertures. Here is the threshold for customized aperture. Here is the circular apertures. So we analyzed the results from both types of apertures and take the best one. Here is exactly the best aperture which produced the lower scatter of points. And it is the PSF model of our data. So do I have to finish? It's 15. Okay. Okay. So there's also a lot of work to do with our data after the pipeline. We have to decorrelate our data with temperature, with position, with, I propose also two PSF coefficients to analyze if the PSF is blurred or not, and with orbital phase, because it can influence our data. And there are three additional parameters. So in our data, as an addition to photometric results, we provide up to 7 additional parameters which can be used for the correlation of data. And they really correlate with the magnitude. So you can see this correlation. And after the correlation, after the correlation, the results are, the spread is well below 1 millimagnitude. I will talk about this in a few slides. So the photometric accuracy actually depends on many things. It depends on the PSF shape, on the temperature we had in observation, on the swinging of satellite, the time span of orbit, because first observations were for the CCDs which were clear, and then the problems appeared. So it's another factor: stability of star tracker, some stray light from Earth, Moon. And here is example, the best and worst case. So look, it is the quality, the spread of an orbital point. So from each orbit we we calculate the average, and this point has this precision. So the red points are theoretical values calculated using the Poisson noise, and here it's not so far. So for some stars, very bright stars, the spread is below 1 millimagnitude. But we have, of course, observations when the temperature was much higher, some problems with Moon and so on. So the spread can reach even 6 millimagnitude. So it's completely a disaster for us to have 6 millimagnitude. Look at the spectra. It is what astronomers do with our data. Because of the fact that you have a lot of points and 3 months of continuous observations, you can analyze the spectrum of our light curve, and the noise level is some fraction of millimagnitude. So the astronomers find a lot of interesting findings in this data, looking for some modes. It's mainly astro-seismology, so this is the main aim of these observations. And there are some findings, so some modes in the beta Cephei stars, some interesting information about other stars in BE stars, tidal effects, and many, many, many more. So we are working with the data now. But there are some publications, 3 technical. The 4th is actually under development as some astronomical examples. So I would like to refer you to those works to know what the astronomers found. Thanks to such precise photometry of brightest stars, we had 2 scientific conferences. So for now, we have 80 stars available on our server. Of course, more is going to be published soon. We have a cookbook for processing for this decorrelations with these additional parameters that we provide. We are still waiting for some proposal till the 1st December. Here is our site. You can go there and look what is available, try to tackle the data. And well, I encourage you for the collaboration in this project. It's still a lot of data which were not processed yet, so there's a lot of work to be done. And in general, about myself, I would like to say that electronic imaging is the main interest, my interest, and in astronomy, but not only in astronomy. So all type of image processing, about noise reduction, pipelines, automation of observation, about electronics. I also develop some cameras and work with this. I'm also interested in high resolution imaging, some techniques, software or also hardware techniques. Recently, I was also involved in some interesting work with meteors. So I know that the time is running out, so I think that's all what I wanted to say. Thank you very much. Here is. I can probably hear. You want to record it? Okay.
A very sound process for the data reduction. I mean, I'm convinced that your data is very delicately selected and processed.
Yes.
But at the end, you say that not all of your data it's already analyzed and not even reduced. Why? It's not an automatic software or automatic process?
I didn't say that it is not processed by me. It was not processed by astronomers. They didn't have time to work with it. So we have plenty of data, and it is like, well, the politics of our mission is that there are some teams that are privileged. They receive the data first, and then after, if they say, well, there's nothing interesting here, so we make it public. So that's why we have only 80 stars made available, published, but a lot of stars are still in their hands, and they are working with it. So it is automatized. It takes about 1-2 days to analyze about 3 months of observation. So as I receive data, I quickly process them, and then it's up to astronomer to work with it. So it is the point where it's stacked.
Yeah, thank you.
One question?
So thank you for the talk. now I understand why you are in Mexico. Because the Mexican flag has also the red color. So
It has, but it doesn't have white.
yeah, well, it has white also.
Yes?
Yeah.
Yes, sorry. Sorry. Yeah, okay. It's also green.
I want to understand a little bit about why did you use that optical design?
I didn't.
It's weird.
It was not up to me. Well, why it's weird? It had to be small because satellites had to be small, and on the other hand, we wanted to have the largest possible field of view, and it was the main requirement for this mission, and this is why the optical system was developed to meet these requirements. So we couldn't afford for larger satellite. It had to be small. On the other hand, we have 5 of them, so we can observe it in 2 different filters. Do you think that it would be better to use, I don't know, smaller CCDs, or what do you suggest about this?
I don't know.
The astronomers just wanted to have the largest field possible with this very small satellite. That's all.
Yeah, it's just because the CCD sounds weird and the optical design sounds weird. I don't know why, but it looks like it could be a little bit more big and make some difference.
Probably it couldn't. It was the framework. It was the nano-satellites framework, which was previously developed by Canadians. Yeah. So we wanted to fit exactly in this box.
Yeah, maybe that's the reason why. Well, thank you.
Okay. Thanks.
I have a question. So you would just mention that you could observe in 2 filters and that there are 5 of these nano-satellites, but it's not clear to me how you observe. Are you observing one field with all 5, or are they independent?
It depends on the decision of decision of directorate of our mission. Before the next year, they plan what is going to be observed. So sometimes all the satellites are looking exactly at the same direction, but sometimes they decide to, well, there is something interesting. So someone made some proposal to observe another star. So one of the satellites look at others. So it is completely, it is customized. It depends on what we want to observe.
So, but you have built-in filters that are different for the different satellites, or are they exchangeable?
No. Each satellite has its own filter. It means initially we wanted to have 6 satellites, 3 with red, 3 with blue. Now 1 is out, so we have 2 blue.
And when you process this data, if they're all looking at the same thing, for example, when you process this data, you do them independently, as if you would have 5 light curves for the one object or the one field.
I do it completely differently. I received images, a stack of images for one star, and I put it to pipeline. And it really, then the points, of course, the astronomers take all the data for a given star and correlate them, decorrelate them somehow, and it's up to astronomer. I just produce the best photometric outcomes possible. The rest is up to astronomers.
Thank you.